Could we reach Alpha Centauri, the shocking speed limit of space? Ever since we first looked up, we've dreamed of visiting the stars, and right there, in our cosmic backyard, is the Alpha Centauri system. It feels so close, like a neighbor just waiting for us to pop over for a visit. But there's a problem, a really big one. The universe, it turns out, has a speed limit, a law laid down by Einstein himself, and it's shockingly slow. This isn't just a technical problem. It's a fundamental rule of physics that makes a seemingly simple trip across the street look almost impossible. Have you ever really, truly wondered what an interstellar voyage would be like? Not a trip to the moon or Mars, but to a whole different star. Alpha Centauri is right there, just 4.3 light years away. But what does that number even mean? Well, if you boarded our fastest ever spacecraft, the Parker Solar Probe, which zips along at an incredible 192 kilometers per second, you wouldn't get there in a few years. You wouldn't even get there in a few hundred. You'd be traveling for tens of thousands of years. We're talking somewhere between 70,000 and 150,000 years. Our entire recorded history, from the first cave paintings to the phone in your hand, would happen over and over and over again before you arrived. That's the brutal reality of interstellar travel. So today, we're going to look at the physics holding us back, and the wild engineering that might just let us cheat the system. The problem isn't just that space is big, it's that it's mind-crushingly, soul-bendingly huge, and we are just slow. To give you some perspective, let's shrink the distance between the Earth and the Sun down to a single inch. On that scale, Alpha Centauri would still be over 4 miles away. Our fastest probes, which we think of as miracles of engineering, would barely be crawling. So, why not just build a faster engine? Just put the pedal to the metal, right? The answer comes from the most famous equation in history, E equals mc squared. But the real knockout punch comes from a lesser-known part of Einstein's theory of special relativity. As anything with mass gets closer to the speed of light, its mass actually starts to increase from an outside perspective. It's like you're trying to push a shopping cart, but the faster you push it, the heavier it gets. As you get closer and closer to light speed, that cart's mass heads towards infinity. And to push an infinitely heavy object, well, you'd need an infinite amount of energy. The laws of physics themselves say only massless things, like photons of light, can travel at the cosmic speed limit. For us, and for any ship we could ever build, traveling at the speed of light is impossible. This isn't just a tech problem we can solve with a better engine or a stronger material. It's a universal law that seems to lock us inside our own solar system. It tells us we can't just brute force our way to the stars. So, how do you solve a problem that's woven into the very fabric of the universe? If we can't break the speed limit, we've got to find a workaround. For decades, the smartest people on the planet have been tackling this, and they've come up with some of the most ambitious ideas ever. Our good old chemical rockets, the ones that got us to the moon, just aren't going to cut it. For an interstellar trip, they're like trying to cross an ocean in a rowboat. You have to carry all your fuel with you, but the more fuel you carry, the heavier you are, which means you need even more fuel just to push all that fuel. It's a frustrating loop called the tyranny of the rocket equation. So, we had to think differently. One of the first big ideas was nuclear propulsion. Back in the 50 seconds and 60 seconds, Project Orion proposed setting off a string of small nuclear bombs behind a ship, literally riding the shock waves. It was incredibly powerful and could have, in theory, gotten a ship up to 5% of the speed of light, cutting the trip to Alpha Centauri to about a century. But, as you can imagine, launching a ship with hundreds of nukes on its back came with some pretty massive political and environmental problems. That led to a much more elegant question. What if you didn't have to carry your fuel at all? What if something pushed you? This is the idea behind a solar sail. Instead of wind, it uses the gentle but constant pressure from particles of light from the sunday. It's slow, but it works. But what if you could supercharge it? Instead of the sun's gentle push, what if you used a ridiculously powerful focused beam of light? This one question led to what might be our boldest plan yet to reach for the stars. This brings us to a revolutionary, almost sci-fi concept called breakthrough starshot. Announced back in 2016 by Yuri Milner and the late great Stephen Hawking, it's a total rethink of space travel. The plan is as brilliant as it is audacious. Instead of one huge ship, you start with thousands of tiny ones, gram-scale nanocraft called starships, each about the size of a postage stamp. These little probes would be packed with miniaturized cameras, sensors, and a communication system. Attached to each nanocraft is an ultra-light, ultra-thin sail, just a few meters wide but only a few hundred atoms thick. This isn't a solar sail, it's a light sail, and it's designed to be pushed by a laser on Earth. And not just any laser. The plan calls for a massive 100 gigawatt phased laser array. That's more power than some countries use, all focused into one perfect beam. For a few minutes, this laser would blast the sails, accelerating the tiny ships with thousands of Gs of force. They would reach a mind-boggling 15% to 20% of the speed of light. At that speed, the journey to Alpha Centauri wouldn't take 70,000 years. It would take just 20 to 30 years. A message from the probe saying, "I'm here," would take another 4.3 years to get back to us. That means we could see the first ever close-up images of a planet in another star system, Proxima Centauri b, within our lifetimes. But let's be real, the challenges are gigantic. First, you have to build that 100 gigawatt laser and get millions of individual beams to fire as one. Then, you have to shoot that beam through our wobbly atmosphere without it getting distorted. The sail itself has to be so reflective that even absorbing a tiny fraction of that energy would vaporize it instantly. Then, during its 20-year trip, the nanocraft has to survive hitting interstellar dust, which at 20% light speed hits like a bomb. Finally, after a super-fast flyby, the tiny probe has to use its own little laser to send data over 4 trillion kilometers back home, a signal that would be unimaginably faint. It's no surprise that as of late 2025, the project is reportedly on hold, having run into the harsh technical and geopolitical realities of building something so powerful. If you find these epic challenges and the science behind them as fascinating as I do, make sure to subscribe and ring that notification bell, because you won't want to miss what we explore next. The sheer audacity of ideas like breakthrough starshot is what drives us forward. It speaks to that part of us that feels like we were born just a little too early to explore the cosmos. If you find these epic challenges and the science behind them as fascinating as I do, make sure to subscribe and ring that notification bell, because you won't want to miss what we explore next. While Starshot grabbed the headlines, it's not the only game in town. Scientists are always asking, yeah, but what if? And their answers are stretching the limits of physics. One of the most exciting new kids on the block is a concept called the sunbeam mission. Instead of a laser, a sunbeam would use a powerful focused beam of relativistic electrons that's electrons boosted to nearly the speed of light. The idea is to have a platform hovering near the sun that generates this beam, pushing a much larger 1,000 kilogram probe. That extra weight means more room for serious scientific instruments, shielding, and a stronger transmitter. Its backers think this could get a probe to 10% of the speed of light, making the trip to Alpha Centauri in about 40 years. It has its own insane challenges, like building a platform that can survive the sun's heat, but it shows just how fast this field is evolving. Other ideas get even more exotic. Pellet beam propulsion would fire a stream of tiny physical pellets at a spacecraft to push it, which could move even heavier ships. And way out on the horizon is the dream of fusion propulsion, harnessing the power of a star in a bottle to zip across the solar system and one day to others. What all these ideas share is that they ditch the need to carry your own fuel. They rely on beaming energy to the ship to finally beat the tyranny of the rocket equation. So, could we reach Alpha Centauri? The answer is a hopeful maybe. Not with today's tech, but maybe with the tech we're just now starting to dream up. Projects like Breakthrough, Starshot, and Sunbeam have completely changed the conversation. They've dragged interstellar travel out of pure fantasy and into the realm of extreme, but maybe, just maybe, solvable engineering. The truth is, most of us watching this will never see a human set foot on a world outside our solar system. The challenges are just too massive, and the timelines are too long. But that doesn't make the work being done today any less important. This is our generation's Apollo moment for interstellar travel. We are living in the time when humanity is taking its first real concrete steps toward becoming an interstellar species. The work of these scientists isn't really for us. It's for a future generation. They are laying the foundation so that one day, maybe even this century, we will send our first emissary to another star. And when that first picture, that first bit of data, finally arrives back on Earth after its long dark journey, it will be the fulfillment of a dream we've had for thousands of years. What do you think is our best shot at reaching the stars? Is it lasers, electron beams, or something we haven't even thought of yet? Let me know your theories down in the comments.